Once, twice, thrice, sold. Okay, cool. Tuesday's ions would have looked like this. Comments, questions, concerns. You have to put the brackets around it when it's an ion. For the ions, the brackets also always have to go around it, and you got to write the charge down. Okay, and then yesterday, so on Tuesday I gave you a method for drawing board diagrams. Yesterday, Mr. Radney should have shown you this. There's a couple shortcuts. Once you're comfortable with the board diagrams, there's ways we can use the periodic table to make the whole process quicker. So these aren't like shortcuts in math where it's just like silly little tricks that don't mean anything. There are two techniques here to make your life a little bit easier, and I'll demonstrate them for you real quick. If you're drawing an atom, the row that the atom is in is always going to be the same as how many shells that thing has on the outside. We talk about that a little bit. And then the valence electrons. The valence electrons are the outer electrons. The number of valence electrons is always going to be the ones column of whatever group you're in. If you're on your phone, please put your phone away. And you fill all the inside shells. So the innermost one has 2, then the next one has 8, and then the next one has 8, and so on. So I'll demonstrate what that shortcut looks like drawing you sulfur here. I'll zoom in on sulfur. So if I'm drawing a board diagram for sulfur, sulfur is number 16. So it's going to have 16 protons. The atomic mass is 32. So to find the number of neutrons, it's going to be 32 minus 16 is 16. And then using the shortcut now, sulfur, if you look at the periodic table, either in yours or one of the two on the back there, sulfur is in row number 3. So immediately we can say, okay, well, row 3, it's going to have 3 shells. And then we can go to the group numbers. Okay, well, sulfur is in group number 16. So we take the number in the ones column. Ones column is a 6. So that's how many outside electrons there's going to be. 1, 2, 3, 4, 5, 6. And then everything inside is just going to be full. So that innermost ring can only hold 2. So let's put 2 in there. The next ring can hold 8. And we're done. That's what the shortcut would look like for sulfur. Yes, is that a hand? Nope. Okay. Yes, Imparis, that's a hand.
So I just have a random question.
Yeah.
If a atom like uses an electron, right?
Yeah.
Can it like accidentally gain it back? So it's like it has like 74 and lost like 1 electron and gains it back.
Can it accidentally?
Yeah, so it's like, like opposites attract, so it'll like still have 1 extra proton, but like electrons, so can it get it back? But it doesn't want to get it back.
Some cans, so this is really interesting. You're asking a similar question to my D block, but you're asking it in a different way. So there's a concept that we're not going to talk about in Science 10 that you'll look at when you do Chemistry 11 or 12. I can't remember where it shows up. Every element on the periodic table there's a ton of different properties. You looked at some of them in grade 9. One of the properties that you may or may not have talked about, depending on who your science teacher was this concept of what's called electronegativity. So every element has a value and a number assigned to it that represents this concept of electronegativity. The bigger that number, the more likely it is that an atom is going to grab onto an outside electron. So some of these things, to answer your question, is sometimes yes, sometimes no. The bigger that number, because the other part of this is, if you remember back to physics in your grade 9 unit, you talk about electricity. Opposite charges attract each other, like charges repel each other. So in every single one of these atoms, you have an attraction between the positive nucleus and the negative electrons. But you also have repulsion between the electrons. So whether or not, because all the electrons are negative and they're in the same space. So the electrons are pushing each other away. The nucleus is trying to pull them in. And depending on that balance between repulsion among the electrons and attraction to the nucleus, well, that will determine whether or not what you're suggesting actually happens. So like with a metal, metals become positive, they want to give that outer shell away. Once they give that outer shell away, there's less electrons outside. So you have a big positive on the inside and less, so those outside, the electrons that are now there kind of collapse down a little bit, and they're happy. They don't necessarily want any other electrons to come in. So they may not spontaneously grab another one. That's why if you're going in, like if you, so an example would be something like magnesium. If you go out into the world and you want to start digging up magnesium, you're almost never gonna find just pure magnesium. It's always gonna be magnesium bonded to something else because it's happy to give that electron to something else and then just stay close to it, like ionically attracted. So if you want pure magnesium, you have to rip off that other stuff, and that's all part of the processing for mining effectively. So the answer to your question, but something like iron, you go dig up iron, that outside layer of iron will almost certainly be reacted with oxygen. You're going to iron oxide on the outside, but everything on the inside is going to be pure iron. And so you're going to have parts of it that do give away and parts of it that we're content to keep. And so there's not a straight answer to, it's not like it's always yes or always no to the question you asked. It'll depend on what's out there. Some of the ones, like the most aggressive ones, are that far, like column 17, fluorine, chlorine, bromine, and iodine, and astatine. That whole column there, they have really, really high electronegativities because they always want to grab. They will almost never spontaneously let one go to become the ion again. They want to grab and they're going to hold on to whatever they get. So the negative ones will almost, I can't say for sure never, but the ones that are negative will almost never revert back to their atom stage. The positive ones, sometimes yes, sometimes no, depending on those values for electronegativity and what else is going on around them in the world. Does that answer your question? Are you satisfied with that answer? Okay. It's a complicated question, but a good one. So that was the shortcut for sulfur. I'll show you the shortcut for the ion. Here's the one I wrote, or what I had Mr. Radin go through with the ion. For the ions, it's important to recognize that if after you've drawn all these, perhaps you noticed it, when you're drawing ions, that outside shell is always full. So the shortcut for the ion is, if that valence shell is always full, there's two ways to fill it. Fill, air quotes. Because either you can fill it by, here, let's look at it, by chlorine here. Chlorine, if I'm trying to draw the atom, chlorine is in row 13, row 3, so it's going to have 3 shells. It's in column 17, so it's going to have 7 in the outside shell. Everything's going to be full. And then chlorine becomes -1 by grabbing another electron in. So chlorine could fill itself by just getting one more electron. If we look at magnesium, magnesium's one where, if you take a look at the table, magnesium is in row 3, so it should have 3 rings, or 3 shells, but it forms a +2 ion by giving that entire outer shell away. So if you give away a partially full outer shell, you now have a totally full middle shell. And so to fill up your outer shell, it looks like giving a partial shell away, or actually bringing more stuff in to completely fill that outer shell. The negative ions will fill it. The positive ones are going to boost that, get rid of it. So a shortcut, a demonstration of this shortcut, I'll draw, which one? Did I draw it already? I totally did it already. No, I didn't. Magnesium, the one I just talked about. I'll draw it. Just the thought process. So it looks like this. If I want a magnesium ion, okay. Magnesium, P equals 12, N equals 12. Now I want the ion. Magnesium should be, or it is in row 3, so it should have 3 shells. But it's positive, so it's going to give that outer shell away. So if it needed 3, I'm only going to give it 2 in the ion phase. Then what's left is full. I put the brackets around the charge and we're done. There's no counting, there's no math. That's it. So those are some shortcuts. Again, you don't need to use them. It's an optional way. Like the periodic table, I mean, students, it takes a long time to actually realize the depth of information that's on that periodic table. You learn a little bit in grade 9, you'll be exposed to more of it in grade 10, but the further you go in your study of chemistry, the more you'll realize how much information is actually packed onto that table. It's kind of insane. It's like it was designed with a purpose, which is pretty cool. Okay, so then yesterday, this was yesterday's lesson. I had Mr. Radney go through ionic and covalent compounds. So it would have looked like this. Something you would have talked about in grade 9 was this idea of ionic compounds and covalent compounds. An ionic compound is a metal atom and a non-metal atom bonding by exchanging electrons. So every single metal atom on that periodic, or metal element on that periodic table is going to form a positive ion by giving away an electron. It doesn't really care where it goes. Non-metals, like here with the example I have on the board here, on the screen here, rather with chlorine, non-metals will like, oh yeah, I'm happy to take that. I will take your extra electrons, I will become negatively charged, we'll be happy. So the sodium here is going to give up the one it wants to give up. The chlorine atom is going to take the one it wants that sodium has given up, and you're going to get 2 charged ions. You're going to get a positive sodium having given up that outer shell, and I wouldn't even draw this empty shell, the empty ring, and you're going to have a negative chlorine. And so this diagram actually is a really good example of the process I wanted you guys to go through. If I give you a compound, I'll give you 2 elements. So here's sodium, here's a chlorine. You draw them separately. And then you're going to go and you're going to say, okay, let's figure out how they bond. Well, this guy here is going to fill the space on that guy's outer shell. So then then we redraw, putting them next to each other, because now you've got a positive and a negative, and you remember back to physics in grade 9, positives and negatives will opposite charges attract each other. And so you'll get this sodium and chlorine that are sitting beside each other, electrically attracted to each other. And if you have more of these things, you could actually have another chlorine up here and another sodium here, and these guys are all going to be attracted to each other in kind of a crystal shape. That's why if you look at salt, like a single grain of salt is actually a little cube. And if you look at salt under a microscope, it's a cube, because you have this whole network of sodiums and chlorines stacked around each other, making little boxes, balancing these charges. The covalent ones were the non-metal, the non-metal, they both want to grab. So they will actually share. In this case, the example that was given here was water. So water is H2O. You've got a single oxygen and 2 hydrogens. So then I'll write it out here. The name is H2O. The 2 tells you have 2 hydrogens, single oxygen. Now, hydrogen's an interesting one. Someone in my Block D class asked the question, and I'll show you guys in a second. How do you know? Because if you, on your periodic table that I've given you here on the inside front cover, how do you know if my hydrogen is going to become positive or if my hydrogen behaves negatively? In the example with water, hydrogen behaves negatively, oxygen behaves negatively. So in a covalent compound, because they're both negative, they want to hang on to what they've got and they share. And so how we draw it is we draw the separate Bohr diagrams. We circle the lone electrons where they would share together. And then we redraw overlapping the outer shells where the sharing is happening. So then I had him go through 2 examples with you. Oh, first I had you guys go through this. Just identifying which ones are covalent and which ones are ionic. Remember to figure out which is which. Ionic is always a metal and a nonmetal. Covalent is nonmetal, nonmetal. Where should I make the note? I'll make the note. I'll have you guys add a note. Let's put it over here. Let's do it right here. Okay, so right here, let's make this note. Hydrogen is negative. So I use the minus sign and then VE. That's a shorthand for negative. Unless it bonds with group 17. As a general rule, hydrogen can go either way. It can either give up that outer electron, becoming positive, or it can take and add to its outer shell, becoming negative. I'm not going to say always, but like 95% of the time. If hydrogen is bonding to anything on the periodic table outside of column 17. So column 17 is fluorine, chlorine, bromine, iodine, and astatine. It's the second last column. Those guys, going back to the conversation, Himparis, that you asked about, that column has such a high electronegativity, it will rip the electron off of hydrogen, forcing hydrogen to become positive. Everything else on the table can't do that. They're not strong enough to do that. And so, again, 95% of the time, hydrogen will remain as a positive ion with everything else. And it'll form a negative ion when it's reacting with group 17. As a general rule. So then I had Mr. Radnai show you guys these 2 examples, just kind of going through the process. If I wanted you to do a Bohr diagram for lithium fluoride, you would have drawn the lithiums, you draw the lithium, you draw the fluoride, you draw, because it's a metal and a non-metal, it's ionic. So you draw the transfer, and then you redraw one next to the other. Yes, Himparis.
Okay, so when you're talking about hydrogen, right?
Yeah.
You said if it bonds with like any other element, it will turn positive.
Any other non-metal? No, it'll stay negative. It turns positive only when it bonds with group 17. Sorry, did I say that backwards?
Yeah.
Regardless of what I said, go with what I wrote. What I wrote is correct. Hydrogen is negative unless it bonds to group 17. It's negative every, yeah, sorry. I think I said it backwards. You're right, Himparis. It's only negative, sorry. It's always negative unless it bonds with group 17. Yeah, that's the right way to say it. Thank you for correcting me, Himparis. What I wrote is correct. What I said was backwards. So then the next one I had you do was O2. O2 looks like this. I've got 2 oxygens. Oxygen's a nonmetal. So I've got 2 nonmetals. So they're going to share. I draw each oxygen separately. And then I find, okay, where are the lone electrons? Let's circle them up. Because they're sharing, nobody's giving. So I'm not drawing an arrow transfer. I'm just drawing this is where they'll share and this is where they'll share. And then you draw the overlap of that outer shell, showing the sharing that's going on between those pairs of electrons. And then he assigned 5 questions. Here are the answers to the first 2. So we had MgO. So I've got a magnesium, I've got an oxygen, it's ionic, so there will be a transfer. The magnesium's giving up 2, which is great because the oxygen needs to. So this guy goes here, this guy goes here, and then you draw, finally, each one, but now this one has no outer shell. It gave it away. And this one has a full outer shell. Brackets, charges, you're done. Cl2 would have looked like this. Well, Cl2, the chlorines are really big. Chlorine's a crappy one to draw, I'm sorry. But they're both nonmetals. So they're going to share that outer, or share that pair. So we redraw with an overlap on the outside. Questions about these two? Anyone want me to go over them? Yeah. Yeah. Right here. This pair represents the one from here and the one from here that gets shared in that outer ring. So it's one from each that's creating that pair. Does that answer your question? Okay. So then on the next page, I gave you some bigger ones. I said, okay, well, BeF2. I have to double check because I'm going to give you guys a task here in a second. I want to make sure I didn't double that up. Did I double that up? Oh, I totally did. No, I didn't. Ah, we're good. Cool. So BeF2. That means you've got one beryllium and two Fs. So there's my beryllium, there's my two fluorines. And this is why we need two fluorines, because the beryllium wants to give up two, the fluorine each wants one. So that beryllium's going to give up one for there, and it's going to give up one for here. Now, I don't know if Mr. Rad and I harped on this yesterday or not, but when you then draw them in their ion stage, you need to stagger the positive, negative, positive, negative. So when you redraw it as an ion, you're going to draw the negative, you're going to draw a negative first, the positive in the middle, and then another negative. Because thinking back to grade 9, if you have two negatives, they're going to repel each other, they'll push each other away. So one fluorine's going to end up on one side of the beryllium, the other fluorine's going to end up on the other side of the beryllium. Because the two fluorines are going to repel each other. These two negative ions are going to push each other apart. So when you draw it full, it should look like this. H2O was the example that I gave you, but then I had you do it again. And then Li2O would have looked like this. You had the two lithiums, a singular oxygen, and then you would have a lithium, oxygen, lithium. I ran out of space, but they should be staggered like that. Comments, questions, concerns on anything I gave you yesterday for homework? Okay, if there are no questions, here's what I'm going to get you to do. I just need to double check one thing. Na2S is going to look a lot like that guy. What's the date? That's a great question. The 6th. It's February 6th. Okay, so here's what I'm going to get you to do. I'm going to take this off the board. I'm going to put this up on the screen. For reasons it might help some of you. There's two PR tables on the back. Now I've got one on the screen that you can reference. How many do I have here? 5, 6, 7, 8, 9, 10. I have 23 of you, and I have 15 boards. You see all the boards are numbered, like the separate sides are numbered, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then it goes to 15. That's because 13 and 14 are over here. Board 13 is on this side. Board 14 is on the back side. Because there's only 25 of you here, I don't think we need all of them. So I won't move the couch and use the other side. What I want you to do is this. In partner, we're going to do 3 of these. I want you to get up on the boards. You're going to practice these things. I'm going to give you 3 examples. I want you to work through the process with a partner or partners. I'm going to walk around. I'm just going to walk around. We'll answer questions. We'll help where needed. I just want to I want to use this as an opportunity to just check and make sure we're feeling good about this stuff. The whiteboards should all have erasers and they should all have pens. That one does not have pens. But the pens are everywhere else. I want each of you to have a pen. I want everyone involved in the process. I don't want one person to just take over. The worst thing that happens is when you have one person on the whiteboard and everyone else is like, Yes, I agree. Yes, I agree. Because the only person who's actually learning anything is the person with the board. The act of who's at the board. The act of actually writing it out helps solidify this cognitively. The other thing I'm going to ask is that we're going to do 3 of these. As you are erasing the boards in between, please do not use your hands to erase on the board. The reason for that is because when you do that, you transfer oils to the board, which makes it really difficult to erase later. That board 1, 2, the reason that black cloud is still there and hasn't totally come off is because people have been using their fist. And I have to go around and I have to spray all the boards again. So to save me some of that work, please use the erasers, or if you need, please use a paper towel. The erasers that are out are all the erasers that I have. So grab a partner or 2 people. Find some board space, and I'm going to start giving you some of these questions. I know the 2 of you like to work alone, so why don't you work alone together on. Okay, so. The first board diagram that I want you to go through the process of drawing is. I would like you guys to draw for me ammonia. Ammonia has the chemical formula NH3. I would like for you to draw for me ammonia. Nitrogen. I would like you to draw for me ammonia. NH3. Whoever wrote N2H, it's not N2H3, it's NH3. Yep. I've got 2 already. Okay, so it's 2. You're drawing me the bonding together. So NH3, 1 nitrogen, 3 hydrogens. Go through the process. NH3. NH3. 1 nitrogen, 3 hydrogens. Don't pair them up. So the nitrogens have 7, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Don't pair them up again. And go through the whole process. Draw me the nitrogens. Draw me the hydrogens. If it's ionic, draw me the arrow to transfer. If it's covalent, they will share. And you demonstrate that with loops. Is NH3 going to be ionic or covalent?
Covalent.
Yeah, so now draw me the final version where those ones you circled are actually overlap with the other shells. So don't erase what you got just on the side next to it. Right at the, redraw it all together. There's 2 hydrogens. 1 nitrogen, 3 hydrogens. These guys careful. This is your nitrogen. As an atom, it should only have 7 electrons. 1, 2, 3, 4, 5, 6, 7. This one shouldn't be here. Oh, I thought it had an action here. But it doesn't have a charge yet. Nope, you start with the atoms. And then, so if you're drawing this, things are going to be, so you've got your hydrogens, that's great. You've got your nitrogen, that's great. This is the ion. Because hydrogen is going to act like a non-metal, and this is working with this column. So it's going to act as a non-metal. That's a non-metal. So this isn't going to fill by taking. It's going to actually share it. This is going to share here. This is going to share here. This is going to share. and then you redraw it with this kind of overlap. No, you couldn't have all that because once it's paired, it's not going to be. Yeah, but we don't. Yeah, it's also there. She's explaining to you why. So the way we so the hydrogen. So these two are connected. If you're drawing arrows, then they shouldn't be overlapping. If this is what this is going to look like, what's actually happening there is sharing. Because so with an H3, that's a non-metal. Hydrogen acts like a non-metal unless it's in group 17. So nitrogen's not 17, nitrogen's group 50. So that guy's going to be negative, that guy's going to be negative. This is correct. This is how it's actually going to be negative. And this is how it's negative. That makes sense? Are you two working together? Okay. And who else? Oh, and Mars? No. Oh, he left? No. Who? Oh, he left. Who's hiding? Yeah, it's good. It's good. It's good. Okay, everything looks good. So you guys, remember, unless hydrogen is reacting with something in group 17, it's going to be negative. This should have been covalent, which means you should have been drawing with the circle and the sharing and the overlap again, which I think we all got to that point. Love it. Okay, here's the next one I want you to do. That's NH3. I would like for you to draw me Na2S. Na2S. Sodium and sulfur. Na2S. Actually, no, I take that back. Don't do that. Oh, pause. I take that back. Let's make this more interesting. I would like for you to draw, I'll say it differently too. I want you to draw for me the compound created when lithium and phosphorus, let's do that one. Lithium and phosphorus bond. How many are you going to need of each? Lithium and phosphorus. Lithium and phosphorus. How many lithiums are you going to need to satisfy the phosphorus? Lithium and phosphorus. You have to decide first if this is going to be ionic or covalent. If it's covalent, they share. If it's ionic, they do not share. Is it ionic or covalent? And how many lithiums are you going to need to satisfy the phosphorus? So if they're sharing, so is this thing ionic or covalent? Which one? Covalent means two nonmetals. Ionic means it's a metal and a nonmetal. So it's ionic. Lithium's a metal, phosphorus is a nonmetal. So it's a transfer then, not a share. So how do we draw the transfer? Yeah. They don't share. So then instead of drawing these loops, we draw arrows showing which way these loops are. So you have two options. Either lithium can give up the 1, or phosphorus is going to give up the 5. They're going to give up the 1. To draw an arrow instead of drawing the picture, use a share. Draw an arrow and put it here. And you got to figure out how to arrange the lithiums around the phosphorus. Love it. Straight. Love it. Straight. Love it. Straight. You only want to add more board space. Yeah, love it. Keep going. Hold on, Luis. You haven't got it last year. Gar and Queen was next. Yeah, she asked me first. Go, and then when. As soon as someone walks through that door. Okay, so looks good. Remember, if it's ionic, so a metal and a non-metal, you're drawing the transfer with arrows. If it's covalent, you draw the bubbles of the sharing. And if I'm going to be really, really picky, I want you guys to, so can you gentlemen step away from your board? Actually, can you guys step away from your board? Can you ladies step away from your board? If you have the space, and we're going to be really, really picky, you want to make sure you arrange, and on an ionic compound, you want to make sure you arrange your atoms, or your ions, so that like charges are separate from each other. So yeah, like what you've done up there, what you guys are doing in the middle there, what's going on these boards here, you've got the one on board 8, the one on that board there. This one up here, you want to separate out those positive lithiums as far as you can. Looks good. Let's do one more. To make it more interesting, the last one I'm going to give you is this. As you guys are erasing, get more space. Okay, here we go. Last one. Be3N2. What? Be3N2. Beryllium 3, nitrogen 2. Draw small. Beryllium 3, nitrogen 2. Drop them small. All put together. Beryllium 3, nitrogen 2. Oh, nice. What are they? Dude, that's nitrogen is like other side of the that's where the ion is not at home. No, ion is the element on it. I mean, yeah, that could be it. Okay. Is it ionic? Is it covalent? If it's covalent, they share. If it's ionic, there's a transfer. And if it's ionic, then there's giving and taking, and things are going to become positive or negative, and you have to arrange them a particular way. Draw them all, put it together. So So then, guys, this last step, it's good. You've drawn the arrows now. Draw individually with the ones that are giving becoming positive, the ones that are taking becoming negative. Yeah, finish it up. What you've drawn there is great. Just finish it. Drop. Yeah. So yards, they are read your last semester too. This is the semester you're at. Oh, we'll get you caught up. Wow. Okay. Oh, come on. So let's give you one of these. When you draw like brackets, it's a redraw. Separate off to the side, and you arrange them so that the positives and negatives are there. When you do shortcuts, the whole thing on the ground. Like this. You drew yours, moving around, and then you redraw, stagger the positives and negatives. This guy though is either positive or negative. How many this guy got? One from here, one from there, one from there. Okay, go. This is my course outline. I'll actually go through this she after you read through this, she says, I've read, I understand. You're figuring it out. And we did a section of relaxation. And we did science teaching. You guys are in block C. So on the bin over there, next to the windows, the C on it is where you head. Welcome. Oh yeah. It's good. It's good. It's good. It's good. Yes, thank you, gentlemen. It's good. It's good. Malik is for real. This shortcut on the map, I would draw. That's all I've done. Well, you did this stuff like this last year? Don't worry, it's not going to be very long. And I'm not right now. No, I want to see that. Yes. Looks like it is. Okay, largely these look great. Return to your desks. Have a seat. Yes. Oh, yeah, yes. Yeah, come on. Erase what you got. Leave the monkeys, please. Erase what you got. Yeah, real quick. Okay. Was this helpful?
Yes, very.
Okay, cool. Especially if you were away yesterday. Was this a helpful exercise? Sweet. Okay. So, we got, what is that, 15 minutes? 15-ish minutes. I think we can all agree that that's a lot of work. And if we can find a way to do less work, that would be better, yes? Okay, so in your booklets, I want you to find me this page. It says Lewis diagrams up at the top. Lewis diagrams. It's, if you can wait, that would be, I mean, it's today's lesson. It's not hard though, so it's your call whether or not you want to use the washer. Okay, so here we go. Short lesson. So, Bohr diagram is a lot of work. You're drawing your math to figure out protons and neutrons. Then you're drawing a bunch of rings and you're putting dots everywhere. I've seen people trying to shortcut everywhere. I get it. It's if you can be sloppy, you'd like to be sloppy. Or if a different teacher gave you a different shortcut, that would be preferable because Dweeduff's not going to do that. There was a guy who saw what you guys saw and developed a way to shortcut stuff. When you're drawing the Bohr diagrams and the electrons are moving around and they're sharing, what portion of each atom did all of that happen in? All of the sharing, all of the transferring happened in a specific part of each atom. Where? In Paris? Just the outside shell. So it could be argued that all of the work you did that was underneath that outside shell wasn't necessary. You could argue, make a very, very compelling argument that that's just a bunch of unnecessary work. So there was a guy, a chemist, G.N. Lewis. He felt this way as well. He said, Bohr diagrams, great, they give us some understanding, but it's a lot of unnecessary work because all we actually care about is what's going on underneath. Sorry, we don't care about what's going on underneath. All we care about is what's going on outside. So what he did is he developed a system. He took Bohr's diagram and he condensed it. He said, we're going to arrange dots, just like Bohr diagrams arrange dots. We're going to arrange dots. But here's how he changed things. He said, instead of doing anything fancy with the nucleus, we're just going to write down the symbol for the atom. Forget the protons, forget the neutrons. I can look that up on the table. I'm just going to include the symbol. So even there, that's the first step to shortening up the work. And instead of representing everything, all we're going to represent is the valence shell, just that outer shell. And we're going to ignore everything that happens underneath. So we're going to put the dots around the symbol for the outer shell as whatever atom you're working with, gets ready to bond. Because that's all we care about is the outside. So I'll show you the difference. Bohr diagram for fluorine. It's going to look like this. Fluorine is atomic number 9. So P is going to equal 9. It has a mass of 19. So the neutrons are going to be that mass 19 minus 9. It's going to give you 10. Fluorine is in the second row, so it's going to have 2 shells. It's in column 17, so it's going to have 7 in the outer shell, and that inner shell is going to be full. That's what a Bohr diagram for fluorine would look like. And that's kind of the process you'd go through to draw it. The Lewis diagram for fluorine, if we use kind of the description that I gave you here, is going to look a lot different. The Lewis diagram for fluorine is going to say, okay, well, I've got a fluorine. We're going to do an atom and an ion. So we got a fluorine atom. Okay, we're going to use the symbol for the atom instead of the protons and neutrons. What's the symbol for fluorine? It's an F. And I don't care what's going on underneath. All I care about is the outside shell. So I've referenced it a whole bunch. We're going to put it in the table here. The group number that you're in is going to tell you how many are in that outer shell. Everything in group 1, so hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, each one of those only has a single valence electron. Group 2, beryllium, magnesium, calcium, strontium, barium, radium, all of them only have 2. Sorry, my eyes are dry. We're not going to do anything in that middle section. We're going to jump straight over to group 13. And we're not going to draw anything past row 3. So for the first 3 rows, group 13 only has 3 valence electrons. As soon as you get to row 4, then it would jump up to 13 valence electrons. We're not going to do that. We're going to stay in the first 3 rows. 14 is going to have 4, 15 is going to have 5, 16 is going to have 6, 17 is going to have 7 in the first 3 rows. And then 18 is an interesting one. 18, you take a look at the ones column, you're like, okay, 18 is going to have 8, except for anything like below row 4 or 4 or down. So krypton, xenon, radon, those ones are all actually going to be 18 or 32, or it's going to be full. So krypton and xenon are the only ones that are going to have 18. Then radon and the one below it are actually going to have 32. But this group 18 really just means that last column on the table really just means it's full. That outer shell has to be full. So how many should helium have? Helium's only going to have 2. Even though it's in group 18, group 18 just means that outer shell is full. So helium will have 2. Then neon and argon will each have 8. Krypton and xenon will each have 18. And then radon and that unnamed lower one will each have 32. The point of group 18 is that they're full. So let's go back to the fluorine atom. Fluorine's in group 17, but it's in the first 2 rows, so it's going to have 7. You put the dots down in the same way you do the outer shell. So we start north, east, south, west, and then you start pairing. 4, 5, 6, 7, and we're done. That's all you have to do. We don't have to do any of the inner rings. So then for an ion, some parts are similar, some parts are different. For a fluorine ion, the Lewis diagram, I still draw the F. The charge on a fluorine ion is going to be what? Take a look at your table. What kind of ion does fluorine form? -1. So if it's going to be -1, let's put the charge up here. If it's going to be -1, is it gaining or losing an electron? It's gaining. So rather than having 7, you're going to have 8. 1, 2, 3, 4, 5, 6, 7, 8. Done. And you throw brackets around there just like we did for the Bohr diagram. But you don't have to draw any of those other shells. So for the really big atoms, like your chlorines, your sulfurs, and your calciums, and your potassiums, this cuts down a ton of work. So some of you guys like instructions, so let's formalize the instructions here. When you're drawing Lewis diagrams, Write the symbol for the atom or the symbol and the charge for the ion. Determine the number of valence electrons for the given atom or ion. The valence electron comes from the group the atom is in. Ions will either be empty if they're positive or full if they're negative. It's all or nothing with the ions, depending on whether they're, so the positive ones are all metals. The negative ones are all nonmetals. You place the valence electrons around the atom or the ion starting at the top, just like we did with Bohr diagrams. You move around the compass, and then you start pairing out until you run out. I'll do 4 examples, and then I'm done. These are quick. We like quick. Here we go. Flip the page. Okay, chlorine atom. What's the symbol for chlorine? Cl. How many, or what group? It's an atom, so we don't care about the charge. It's in 17, so it's going to have 7. 1, 2, 3, 4, 5, 6, 7, done. Beryllium. Someone said it already. Beryllium is Be. What group is beryllium in? 2. So it's going to have 2 valence electrons. 1, 2. Done. Ooh, that's a great question. If it's the first, the only one that has 2 in the first shell is which one? There's only one atom that has that. Someone help him out. He's asked. This is a really good question. In fact, it's part of the homework that I gave you. So he's actually asking a question that's going to, I try to throw a trick at you in the homework. There's only one atom on there that has 2 in the first shell. What is it? Helium. If there's 2 in the first shell, that first shell can only hold 2. You wouldn't separate them, you'd pair them. So for this question down here as part of your homework, that was my trick. Good question. If it's in the first shell and there's 2, you would pair them up immediately because there's no space to go around. Good question. Okay, bromine, the ion. Bromine has the symbol Br. Bromine is in column 17. So an atom would have 7, but the charge on bromine is -1, so that means it's going to have 8. 1, 2, 3, 4, 5, 6, 7, 8. It's an ion, so you put the brackets and the charges outside and you're done. The last one is calcium. Symbol for calcium is Ca. We want the ion. So if it was an atom, calcium would have how many? 2. But it's an ion. What's the charge on calcium? So calcium has given up those outer 2. So there's nothing in the valence shell. This is done. You wouldn't put any dots because that valence shell is empty. And that's it. I want you guys to do these 9 for, well, you will certainly be able to finish them, Lexi. You can go to the washroom if you like. These 9 I'd like you to do for homework. You can definitely get them done in the next couple minutes. And when the bell goes, you may also go. Have a great day. We'll see you later.